Welcome to the debate. Imagine spending billions of dollars to build the ultimate pair of glasses, right? You launch them into the vacuum of space, you turn them on, and, well, you realize you got the prescription wrong.
Yeah, which is exactly what happened 35 years ago.
Right, April 1990, the Space Shuttle Discovery deploys the Hubble Space Telescope. And for a long time before that, the paradigm for space exploration was just so rigid. You know, you launch a satellite, and it's a pristine, sealed vault.
Right.
If it breaks, it dies. But Hubble broke that rule entirely. It was designed from the ground up to be visited, to be touched, and, upgraded by human hands in orbit.
And honestly, it's a good thing it was, or we'd be talking about the most expensive piece of space junk in human history.
The rescue missions.
Well, that's what we're debating. Were these highly complex human repair missions a brilliant, adaptable design choice? Did they represent a profoundly wise financial investment of international resources? Or, as you might say, were they fundamentally reactive, resource-heavy rescue missions necessitated by a flawed initial deployment?
I think you know where I stand on that.
I do. And I will be arguing that designing Hubble for astronaut servicing was an absolute masterclass in investment strategy. It transformed a static satellite into this living, evolving laboratory. It exponentially increased its lifespan and gave us an unprecedented return on investment.
Well, while the scientific output of Hubble is absolutely undeniable, no one is arguing against the science.
Right.
But the romanticized narrative of these, heroic servicing missions, it obscures a much more pragmatic and frankly concerning reality. I will argue that tying the functionality of a flagship scientific instrument to continuous, high-risk human repair missions was an incredibly resource-intensive model.
Okay.
It was born out of sheer necessity and baseline hardware failures rather than some ideal visionary design philosophy.
Let's get right into it then. To me, the servicing missions are the ultimate force multiplier for astronomical discovery. You have to remember that Hubble was explicitly designed and built for this.
It had the handholds.
Exactly. There were handholds and modular bays built into the chassis before it ever left the ground. That foresight didn't just allow the telescope to outlive its original, I think it was a 15-year estimate.
Yeah, 15 years was the baseline.
Right, so it meant we could install cutting-edge technology that literally did not exist in 1990. By the time of the final servicing mission in 2009, Hubble was at the absolute apex of its scientific capabilities. We are talking about an investment that directly led to over 1.6 million observations.
It's a huge number.
20,000 scientific papers and a Nobel Prize in physics. The adaptability is the mechanism of its success.
Okay, but we have to look at what triggered that mechanism in the first place. The astronomical community and the public, they've completely fallen in love with the romance of the spacewalking astronaut saving the day.
It is a great story.
It is, but let's look at the catalyst for that first mission in December 1993. Immediately after launch, it became apparent that the telescope was fundamentally crippled. The primary mirror suffered from a spherical aberration.
Which sounds highly technical, but it really just means it was ground slightly too flat, right?
Too flat at the edges by about 1/50th the thickness of a human hair.
Wow.
Yeah, it sounds microscopic, but in the unforgiving physics of optics, it meant the telescope couldn't focus light to a single point. It was essentially nearsighted.
Right, the early images were fuzzy?
Exactly. So servicing Mission 1 wasn't some visionary, planned upgrade. It was a multi-billion-dollar emergency rescue mission.
Well,
they had to fly up there and install COSTAR, the Corrective Optics Space Telescope axial replacement, along with a brand new wide field and planetary camera, just to get the telescope to function at the baseline level that was promised to taxpayers years earlier.
I hear the frustration in that, and I know people were calling it a techno-turkey at the time.
Oh, late-night hosts were having a field day.
They were. But I look at that exact same event, and I see it as the ultimate proof of concept.
How so?
Because if Hubble had been designed under the traditional sealed vault paradigm, that microscopic manufacturing error on the mirror would have ruined everything.
Sure.
The initial investment would have been a total write-off. Because the architecture was modular, we didn't just abandon ship, we fixed it.
but look at the physical and financial reality of what it took to not abandon ship.
Okay.
You have astronaut Jeffrey Hoffman in the vacuum of space, right? In zero gravity, having to carefully maneuver the original camera out and slide its successor in.
Right, the new wide-field camera.
And this is a wedge-shaped instrument the size of a mini grand piano.
Yeah, it's huge.
Now, sure, it's weightless in space, but it still has a mass of over 600 pounds. It still has exactly the same momentum it has on Earth.
Right, physics still apply.
Exactly. If he pushes it too fast or bumps it against the telescope's internal struts, the delicate inner workings of the observatory are completely destroyed.
But he didn't.
He didn't. But the precedent this sets is staggering to me. We tied up the Space Shuttle Discovery, we committed massive international capital, and we risked human lives to correct an earthly manufacturing mistake. As an investment strategy, spending that much money just to get what you originally paid for is a cautionary tale.
Wait, stop right there, though. You're framing it entirely around the cost of the initial mistake, but you're completely skipping over how they fixed it.
They put in a new camera and corrective mirrors.
Right, but they didn't replace the flawed mirror itself because that was impossible. It's the structural core of the telescope.
Yeah, they couldn't just swap the primary mirror.
Instead, they used CoStar. They essentially installed a microscopic pair of contact lenses in front of the instruments to perfectly counteract the mirror's flaw. That is sheer engineering genius.
It is clever, I'll give you that.
And once that infrastructure for human intervention was proven to work, every subsequent mission stopped being a rescue and became an evolution.
Well, I wouldn't say they entirely stopped being rescues, but go on.
Just think about the technological leaps. In Servicing Mission 2, this was in 1997, the astronauts didn't just tighten screws, they completely expanded the telescope's vision.
They added the spectrographs.
Exactly. They installed a new spectrograph. And for the listener, spectroscopy isn't just taking a pretty picture.
No, it's the real science.
It's splitting light into a rainbow to read the exact chemical fingerprints of stars and galaxies. They pushed Hubble's vision into the near-infrared and ultraviolet. And then, in 2002, during Servicing Mission 3B, they installed the Advanced Camera for Surveys.
ACS, yeah.
That single instrument multiplied Hubble's discovery power tenfold.
It did. It was a massive upgrade. But my issue is with the narrative of these smooth, flawless upgrades.
But they unlocked entirely new fields of science. Because of those specific camera upgrades, we got the Hubble Deep Field.
The deep field is iconic, yes.
Think about how this actually worked, though. Astronomers pointed the telescope at a patch of sky in Ursa Major that looked completely empty, just pitch black.
A huge risk at the time.
A massive risk. To see anything, Hubble had to hold perfectly still for 100 hours of continuous exposure time.
Which is a lot of highly valuable telescope time to spend looking at nothing.
Exactly. But the newly installed cameras were so incredibly sensitive that they could catch faint individual photons that have been traveling for over 10 billion years.
Yeah.
Out of that darkness, they discovered 3,000 galaxies peering back to the universe's dark ages. You simply cannot get that kind of transformational science without the physical ability to swap out 1980s technology for 21st century sensors.
I am not denying the majesty of the deep field. It fundamentally changed cosmology. We went from wondering if there were other galaxies out there in the deep past to seeing thousands of them in a space the size of a pinhead.
Right? It's mind-blowing.
But let's pull back the curtain on the mechanics of these missions. You mentioned the 2002 mission.
Servicing Mission 3B.
Yeah. To get that new camera in, the Space Shuttle Columbia had to fly up, and an astronaut had to use a massive robotic arm to physically grapple a school bus-sized telescope traveling at 17,000 miles an hour.
Right, the Candid arm.
They had to wrestle it into the shuttle's cargo bay and lock it down before anyone could even touch it. The infrastructure required to do this is breathtakingly expensive. And let's look at the much heralded Servicing Mission 4 in 2009.
The mission that brought Hubble to its absolute peak.
Yes, they installed 2 incredible new instruments. But what else did they have to do? They had to perform the first ever on-orbit repairs of failed internal instruments.
They fixed the Advanced Camera for Surveys.
Right. We aren't talking about sliding a grand piano-sized camera into a slot anymore. We were talking about astronauts in pressurized, bulky spacesuit gloves having to unscrew tiny non-captive screws, to open sealed instrument panels.
It was delicate work, for sure.
That was never part of the original modular design.
And yet, they succeeded?
They did. But the financial and operational logic here is what we are debating. Maintaining the single observatory required the full weight and infrastructure of the crewed spaceflight program.
I don't see why that's a bad thing.
Because when we evaluate this as a financial investment, we have to seriously ask if tying astronomical progress to the immense, costly, and dangerous infrastructure of the space shuttle is truly the most efficient path forward.
I actually think it is, because separating the cost of maintenance from the value of continuity is a false dichotomy.
What do you mean?
Well, the return on the investment of international tax dollars is unprecedented, exactly because of the longevity those servicing missions provided. Hubble didn't just take one-off snapshots.
Okay.
It provided a multi-decade, continuous timeline of cosmological phenomena from a single evolving platform.
But is that multi-decade continuity from one specific telescope truly more valuable than having launched, say, 3 separate, highly specialized, cheaper telescopes over that same 30-year period?
Absolutely, because you are calibrating against the same baseline. Look at our own solar system. From 1992 to 1999, Hubble captured a continuous series of observations of Jupiter's Great Red Spot.
The big storm.
Right. This is a high-pressure storm twice the size of Earth that has been swirling since at least the 17th century.
Yeah.
Because we kept Hubble maintained and calibrated, it was able to definitively prove that the Great Red Spot is shrinking.
Right, it's changing shape.
It's changing its wobble, and its outer winds are actually speeding up. We know that because we had the same eye looking at it for a decade. Or look further out to supernova 1987A.
The star that exploded right before Hubble launched?
Exactly. It was the brightest exploding star seen in 400 years. Just 4 months after Hubble's launch, the telescope resolved an elliptical ring of glowing gas around the dying star.
I remember those images. They looked like a pearl necklace.
Yes. And because we kept Hubble alive through 5 servicing missions, astronomers have watched the shockwave of that explosion hit the surrounding gas in real time. As of recently, Hubble has collected something like 7,000 data sets on that one object alone.
That is impressive, I admit.
We are watching the complex dynamics of a star's death play out over decades. That kind of long-term continuity spanning entire careers of researchers. It's just impossible if you are just launching disposable, short-lived satellites.
I concede the value of the long-term data sets. The work on 1987A is a treasure trove for astrophysics. And to be fair to the investment, we also have to acknowledge Hubble's role in the bigger cosmological questions.
Like the age of the universe.
Right, and supermassive black holes. By studying the rapid rotation of a disk of hot gas in the core of the galaxy M87, Hubble was the instrument that finally confirmed supermassive black holes actually exist.
Exactly.
And when it launched, we didn't have a single confirmed planet outside our solar system.
0 exoplanets in 1990.
0. And now we have thousands. And Hubble was the first to detect basic organic components like sodium, carbon dioxide, and water vapor in the atmospheres of those exoplanets.
Which perfectly illustrates the compounding return on investment. The longer it stays up and the better we make the instruments, the more fundamental the discoveries become.
But here is where we diverge. My argument is that these staggering triumphs occurred in spite of the telescope's physical fragility, not because of it.
In spite of it?
Yes, we praise the servicing missions for allowing us to look deep into exoplanet atmospheres. But we gloss over the fact that between those scientific milestones, the telescope was constantly breaking down.
Well, things wear out in space.
But over the 16-year servicing period, immense resources were spent simply keeping the patient on life support.
I wouldn't call swapping old parts life support. It's maintenance. You change the oil in your car, right?
Changing the oil doesn't require a space shuttle. It was life support. They had to replace a cryocooler.
Oh, the NICMOS cooling system.
Yes. For the listener, a cryocooler is essentially an ultra-cold refrigerator needed to keep the telescope's infrared sensors near absolute zero.
Right, because heat generates infrared light.
Exactly. If it warms up, the sensors get blinded by the telescope's own body heat. When that failed, a whole segment of Hubble's vision just went dark until the shuttle could get up there.
But they fixed it.
They had to replace failing solar arrays. They had to replace 6 different gyroscopes just to keep the telescope pointed straight. You are praising the fact that we had to send a multi-billion-dollar space plane to replace gyroscopes.
It's part of the modular design.
If we look at this strictly as an investment philosophy, it is a glaring cautionary tale about hardware reliability. We tied up decades of human spaceflight capabilities to continually repair a deeply fragile asset.
I think calling it a fragile asset or a sunk cost entirely misses the reality of how scientific paradigms shift.
How do you mean?
The questions astronomers were asking in 2009, when they performed that final servicing mission, were fundamentally different from the questions they were asking in 1990.
Sure, science moves on.
Right, so no unserviced or reliable satellite could have adapted to that shift in human knowledge. It's not just about keeping the lights on, it's about changing the nature of the data we collect.
Okay.
By the end, Hubble was taking multi-wavelength images where different cameras layered data, blue for hot stars, aqua for energized gas, pink for glowing dust.
Composite images.
Yes. That level of nuanced, layered data collection is a direct result of the instruments we brought up to the telescope long after it launched.
The instruments are brilliant. I'm not arguing that. The delivery mechanism is highly inefficient and needlessly dangerous.
Dangerous?
Absolutely dangerous. Every time a shuttle launched to fix Hubble, we were operating on the razor's edge of disaster. The physical architecture of Hubble was incredibly delicate. For instance, the telescope was designed with cross-shaped struts that hold the secondary mirror in place.
Which is what causes those beautiful cross-shaped diffraction spikes on the bright stars in Hubble photos.
Exactly. Those spikes aren't real. They are visual artifacts caused by light bending around the physical hardware.
Right.
It's a beautiful quirk, but it reminds us how physical and delicate this machine is. When we talk about investment, any honest accounting has to factor in risk.
Okay, let's talk about risk.
The risk profile of the Hubble servicing missions was astronomically high. If a servicing mission failed, not only could we have lost the entire scientific asset anyway, but far more importantly, we could have lost the astronauts.
Well,
The space shuttle program was not perfectly safe, as history has tragically shown us. Tying our premier astronomical platform to the inherent dangers of crewed spaceflight is a massive liability.
but they didn't fail.
They were lucky.
No, they didn't fail because the design fully accounted for the human element. The engineers at Marshall Space Flight Center who originally built it, and the teams at Goddard who designed the specialized astronaut tools, they built a machine explicitly meant to interface with human hands in the harshest environment imaginable.
And it was a massive effort to make those tools work.
Exactly. But that isn't a flaw. It is one of the most profound engineering achievements of the 20th century. When astronaut Jeffrey Hoffman had to be meticulously careful moving that heavy camera, he was able to do it because the rails, the handholds, and the entire system were engineered for that exact physical intervention.
Engineered for it, yes, but reliant upon it to a fault. And I think that perfectly encapsulates where we diverge on the concept of this investment.
How so?
You look at Hubble and see a dynamic system that gracefully accepted upgrades, validating its design. I look at Hubble and see a fragile system that demanded a constant IV drip of international capital and human risk just to fulfill its basic mandate.
I see.
What other completely new technological paradigms or entire fleets of cheaper, specialized observatories could we have funded if we weren't locked into the immense gravitational pull of maintaining this one specific telescope?
That is a fair question. And as we draw this debate to a close, let's summarize our positions based on that.
All right.
My perspective remains firmly that the 5 servicing missions were a brilliant, unparalleled financial and scientific investment. By designing Hubble to be serviced in orbit, NASA and the European Space Agency transformed what would have been a static, eventually obsolete piece of hardware into a living, evolving observatory. But that modularity allowed us to recover from a critical initial setback and ultimately uncover phenomena like the atmospheric composition of exoplanets and the age of the universe that weren't even on the radar at the time of its launch. The servicing missions were the very mechanism of its greatness.
And my summary is that while the scientific output of Hubble is nothing short of extraordinary, the requirement of 5 highly complex, resource-intensive space shuttle missions to fix aberrations and failing components is a cautionary tale.
Okay.
It highlights a design philosophy that placed an immense logistical and financial burden on the space program. Yes, the breathtaking images and the million citations were achieved, but they required a perilous, reactive model of constant physical intervention. It's a model we should think very critically about before ever replicating.
However, despite our deep disagreement on the investment philosophy today, I think there is a profound point of convergence for both of us.
I think I know where you're going to say.
Regardless of whether you view the servicing missions as visionary upgrades or high-stakes rescues, neither of us disputes the human element. The sheer ingenuity of the astronauts who performed those zero-gravity spacewalks and the thousands of scientists and engineers across the globe who supported them resulted in one of the most transformative scientific endeavors in human history.
I completely agree with that. The personnel who managed the hardware, the tool development, and the flight operations, they achieved something genuinely miraculous.
They really did.
The dedication to keeping that telescope at peak performance, despite all the challenges we've discussed, is a profound testament to global cooperation and human tenacity.
And yet, as much as we have explored today, from the changing winds of Jupiter's Great Red Spot to the deepest, darkest fields of Ursa Major, we have to remember the sheer scale of what is left to find.
Oh, it's vast.
Despite 35 years of continuous data collection, despite more than 1.6 million observations, the Hubble Space Telescope has only looked at 0.1% of the universe.
Wow. It really puts the cost, the risk, and the effort into perspective.
It does. And as we look toward the remaining 99.9% that still awaits discovery, we are left with a vital question. Will the exploration of that vast unknown rely on the living, serviceable, slightly leaky research stations we build in the dark? Or will it require an entirely new technological paradigm?
That is the ultimate question for the next generation of astronomers.
Until next time,